So the topic today will be to look at how U-SQL as a framework allows you to scale out your custom code that you have written in .NET, but even in Python and R at scale in Azure Data Lake. I will basically go and first talk a little bit why this is important and why we actually designed U-SQL for that purpose, to basically make that easy for you to do. And then we go through a couple of examples. The first example I will show is actually how we give you the ability to use some of the cognitive services libraries by installing them into your data lake. There is an easy way for you to do that through the portal. And if you install those, you can basically use some of the cognitive services APIs. These libraries are basically implemented using the exact same extensibility mechanism that you have at your fingertip as well. And so I will then also show you how you can actually do that by yourself, both first going through a little bit the extensibility framework at some level, and then show you an example of me actually writing some custom code, processing the same images that I will be using for the cognitive library example as well. Just to show you that basically one of the data lake promises, meaning that you can have the original data and schematize it on read based on your different needs, actually really comes to play here. And then I will also show you what the current state is about how to scale out Python with U-SQL and R with U-SQL. And I will go and probably also talk a little bit, if you have time, about some of the things that we are thinking of going on in the future. So if you look at what the characteristics of big data analytics are, is that we have done big data analytics in our own data lake within Microsoft for the last 10 to 12 years. In particular, we have several different business units inside Microsoft doing interesting stuff with it. So for example, we have the digital crime unit, which is an organization within Microsoft that is basically analyzing a lot of web traffic and log records, etc., to try to identify botnets and take them down. You might have heard in the news sometimes that Microsoft helped the FBI or Interpol or somebody else to take down botnets, and that was basically that group that is doing that analysis. Now, in order to be able to do that analysis, they use a lot of complex custom algorithms inside the lake to analyze the data. Another example is Bing is doing searching over images, as you probably know. And that means it needs to have this image tagging capability, similar to what you will see in the example later, but also creating thumbnails, etc. So they have kind of the same kind of feature extraction and classification requirements, and for that they use custom code to do so. And so one of the core kind of real big data characteristics for us is that you not only need to be able to operate on all kinds of data, including images, including semi-structured log records, including potentially structured data, but you also want to bring your own code to do the analytics. It's not us, the platform offerer, that knows all the different formats and knows all the different algorithms that you might want to run against the data. Actually, you might want to develop custom algorithms that are giving your business advantage and your business rules into the lake without us being able to actually do that for you. So the important part for us is to make it very easy for you to add your custom code and then give you the scalability framework to scale it out across any size of the data and execute the code efficiently. So basically, bring your own coding expertise and scale it out. So how does that work? Well, if you look at existing SQL languages in the big data space, let's say Hive or SQL-MR and PigSQL and all what they're called, they are very good at giving you an abstraction to make scale out easy, because it's a declarative language. You normally don't have to tell me how to execute, just what to execute. And it's the power of SQL, basically. So that's very easy. But the extensibility model is often a little bit hokey and not very easy to use. Let's say in Hive, if you want to add a user-defined aggregator, you have to patch the Hive server. If you want to add a user-defined, if you want to add a SERDI, for example, it is a fairly complex piece of code that you have to write in Java to do so. So it's not that easy to extend this, and the extensibilities often have like a bolted-on feeling, etc. Let's say in SQL MR, you have to write the mappers and reducers, and you have to really understand how the scale-out infrastructure works to be able to make that work efficiently. So if you look at programming languages for big data, and that goes down from like the MapReduce layer up to something like the link-like expressions that Spark has in Scala and Python. The extensibility, of course, is very simple. You write it in your custom code environment. However, you're not getting a lot of scalability and declarativity because you basically have these islands within your custom code. And so your custom code doesn't scale out. It's just that you scale out the data processing, and then you bring the data in. Now, Spark has added some libraries and some extension mechanisms that make it easier as long as everything fits into memory. So they are maybe a step further than most in that space, but it's not an easy way for me to scale out my code, because my code encapsulates the declarativity islands, the scale-out islands. So we think that U-SQL basically gives you the benefit of both. It gives you the declarativity that makes it easy to not have to worry about the scale-out, and it gives you an easy experience around extensibility, so to make it kind of equally native. So what we actually do is we basically have this U-SQL framework that now takes your custom code written in .NET, Python, R, etc., and scales it out in a declarative SQL-based framework, so that you don't have to worry about the topology of your scale-out architecture. So let me show you an example of a U-SQL script here. What you see here is on the left-hand side, you see a script that just does some stuff, like it does an extract, a select, output, process, etc. And then on the right-hand side, you see like an equivalent job graph that could be generated out of this script. So if we look at this, you see a couple of places where we basically have our declarative framework that then embeds the custom code. So for example, we have the extract statement, extract from using, that is then translated into these extract nodes. And that's part of the declarative framework. So that's part of the language that we provide you with. However, we have this extension point both inside the select statement and within the extract statement, where you can bring in your own code that then gives you the ability to do something. So in this example, the extract statement has a custom extractor, and then the select statement has a custom function that is being invoked. And as if you look at it, it's just basically C# expressions. And that's because U-SQL uses this .NET type system and uses then C# as its expression language. Now, this might be confusing for people that come with a pure T-SQL or SQL background, because SQL has its own type system and its own expression language. So people are primarily confused, for example, about equals being the equality comparison. But it makes it very simple for you to invoke custom code. And then the same with process, which is another so-called user-defined operator. Again, you have a place where to put in your user code, and that user code then gets executed at scale. So let's just go back here quickly and zoom in. If you look closely here, you see this extract node, for example, has 70 vertices. So that means it actually now scales out your user code onto 70 nodes and operates on 70 subpartitions of the incoming data to actually do your processing. And in the script, if you look at it, you didn't notice anything about how many nodes it needs to take, etc. You're just having a SQL-like expression there. And so that can continue. So you also have like custom outputters and the ability to basically scale that out as well. So now this scale-out capability we have used also to actually give you some built-in capabilities or additional capabilities, extensions that you can install. And that's our cognitive library APIs. So the cognitive services people gave us some of their models snapshotted, I think, November 2016, around the time we went GA currently, plus their algorithms. And we now package them into our extensibility mechanism and give them to you in form of some of these user-defined operators like extractors, appliers, processors, reducers, etc., depending on what the semantics is of what they do. So let's take a look at an example. And most of the code are like either documentation or code is available on these links that you see on the slide deck there. So let me go and show you the cognitive processing here. What you see here is that I referenced the assembly, image common, and image tagging. Where did I get that from? When you are in the Azure portal of your Azure Data Lake Analytics accounts, there is a link called Samples. If you go into Samples, there is a sublink that says Install U-SQL extensions. If you install that, it takes about 10-15 minutes to install because it has to copy a couple of files and install them in the metadata service, etc. You will now have inside your master database and DBO schema, you will now have these assemblies installed. And you can use them. And you can, for example, install them in a common ADLA account so that other people can use it as well, if you so choose. So in this case, what I decided is I use the image common and the image tagging assemblies that are part of the installation using my reference assembly statement. And that allows me now to use the corresponding image tags extractor from the cognition vision namespace and class. So what does that mean? It now gives me the ability to take images and find the number of objects in them, as well as the concepts that it finds inside the images, as well as the corresponding confidence that it has that this image actually contains this concept. So that's basically what I'm extracting here. And then I'm also projecting the name and the format, which I get from these sample images. So let's take a quick look at the images that I'm processing. I have here a local copy of the images. You will notice there are some JPEG files and there are some TIFF files. The TIFF files are primarily there to show you that I can exclude them from processing fairly easily, and I will show you that in a minute. And to give you a 1960s throwback, I guess, based on the age of those images. If you look at the JPEG images, let's take a look at 9617. Let me open that quickly. And you kind of notice there is a squirrel sitting on a rock inside some forest landscape. Let's see what these cognition image tagging capabilities actually can infer from the picture. So I'm basically having them loaded into this folder, samples, data, images, and I'm kind of mapping them to name and format. So this is our file set option that allows us to operate over a set of files. These lifted parts of my file path into the columns can be used as normal columns, so I can, like in this case, concatenate them back into a full file name. But I can also use them in predicates. So in this case, I'm saying only operate on the images that have the format JPEG in some form of spelling. Now what that means is you see they are in different statements. So you would think that maybe I do first the extraction over all the data and then I filter it down. But that's not how U-SQL works. U-SQL actually will combine the statements into one big statement, and then it will push this predicate up into the previous statements. So in this case, it will actually push it into the extract framework and tell the extractor only operate on the files that actually have, in this case, a format of JPEG. And so what it then will do is it will completely ignore the TIFF files. It will not even open them. It will see the metadata and then discard them. So that gives us a pretty efficient processing of a large set of files if I only want to see like a certain subset of it. Well, and after having done that, I do some additional processing here primarily I'm mapping this SQL map back into a textual representation. If you look at this, you will notice this is just pure C# porn. So this is like a lambda expression with within a link select expression that then does a string join over it. This is just serializing the map into a single string. So I can take a look at it when I output it. So I did already, just before we started, I submitted a job here. When we look at the job, you notice that it was actually only reading the 15 JPEG files. It was completely ignoring the other files. And it was operating here on 2 vertices. It took about 17.7 seconds per vertex to do the processing. Now, in order to be able to do that, I had to use some preview capabilities on like better file set processing, grouping files together, and so on. If you look at the code, you will see a little bit more detail what I did here. But that gives me basically really high scalability of operating over large files, even if they are not very big. Like, obviously, JPEG files are in the kilobyte to megabyte range and not in the gigabyte range. And then down here, I have the aggregation for like the output that took about 7 seconds. So if I open now the result file here, let's see what it found for my squirrel. Let me open this up here and look for 9617. It's here at the top. So it found 8 objects, and if you look at the objects, it found like animal, good, with 96%, bushes, forests, grass. It even found a mammal here. It also found out that it was obviously outdoors and that there were trees involved and wood, etc. It didn't find the rock, interestingly enough, and it didn't notice that the mammal was actually a squirrel. Now, that later part is probably because the model that we got from the cognitive team is not precise enough to go down to the level of like differentiating a squirrel from any other mammal. But it was pretty impressive. Like I was first wondering, how did it notice that it was a mammal? But it must have like recognized the fur or so. Now, it's not always good. So if you look, for example, at this image here, which is a lion or turkey fish from above, and he's like spreading his stuff, actually didn't recognize it as a fish. That's 46, 45. Let's see, that's down here. Oops, one up. It actually thought it was an arthropod, which is, I don't know, quite sure what type of animal it is. It's probably something that crawls along the floor, because it got completely confused by those spines sticking out. It was, however, still with 1% confidence identifying that it might have been on top of the ocean floor, so that was still impressive. But this just shows, like, it's awesome to do cognition, but don't trust it. So all the things that we have heard the whole week about like how great cognition is, etc., you still have to make sure that you can trust it, which is not always the case. So this is just showing you how to use this, cognition at scale. And obviously, you can imagine you can scale this out over a large amount of data. Oops, what is coming up here? Let me get rid of that quickly. So now what do we actually have available? We do have available the face SDK that gives you the age and emotion detection, the image tagging, even OCR, so you can translate images to text. And what they do is they do not call the APIs. That's for 2 reasons. One is if you would have 1 million objects inside a U-SQL table and you will apply that in a single script, you would have a distributed denial of service attack against these APIs in no time. So that's why we don't do that. The other reason is that obviously you don't want to call and pay for every call for your object. You just want to like execute it at scale efficiently and not have REST API calls going back and forth. So that's why the code is actually running directly inside your data lake account. Now, we also have text analysis, text sentiment, and text key phrase code as well. we might be adding additional code to it. If you have anything that you want to have from us, please let us know. And also please let your friends in the cognitive services team know that you want to apply that in the data lake so that they are willing to share the code with us. We do have some limitations around how big the models are that we can currently deploy, and some other things that we are working on relaxing over the next year or so that you can even use bigger models for applying there. Just to give you an example of how crazy it can get, this is the code that we often use for a VP demo, which is called the so-called mega face demo. So there's a U-SQL table containing 1 million face pictures of people. And what they do is they basically do sentiment analysis and identify the faces and emotions in images and find out which tags are associated with happiness in this. This normally runs in a few minutes over 1 million images. It's pretty impressive. The main problem, though, it's highly scalable. So every time we run the job, it's about $8,000 worth of compute that we use. So we leave that to the VPs to demo, because it's their cost center, not mine. So this was just really showing you how powerful that extensibility mechanism is. So let's take a step back and kind of summarize some of the extensibility models. We do have the ability to obviously have inline C# expressions in select expressions. We do have user-defined functions, UDFs, currently written primarily in .NET. We also give you .NET user-defined aggregators, and we give you user-defined operators, which are the most powerful category of things that you can write in .NET, Python, or R. So let's take a look at what are these user-defined operators. We already seen one of them, which is basically we take an extractor which takes byte arrays or files and turns, or parts of files, and turns them into row sets. We also have user-defined outputters. They do the inverse. They take a row set and put it out into files. Then we have processors. They take a single row, so they take a row set, they take one row out of the row set and produce 0 or 1 row out of it. And then you have different models in terms of doing pass-through versus transforming the whole row. So pass-through means that it might only operate on a subset of rows and then just pass through the rest of the row. Then we have user-defined appliers. It's like a processor, but it takes one row in, and it outputs 0 to n rows. The main reason why we differentiate that is one is that it allows our optimizer to have better cardinality estimation. So if you give me a processor, I know that I'm not going to explode, so my cardinality will at most be the same. While if you give me an applier, the optimizer assumes that you actually have an explosion of rows. The other thing, of course, is the appliers are currently used with cross-apply or outer apply inside the statements. Then we have user-defined combiners, which is like user-defined joins that take 2 row sets in, combine them into one. We have user-defined reducers, which is kind of the most generic one. A reducer takes a partition of data, a set of rows that have been logically partitioned by the reduce statement, and it outputs another set of rows. Now, often that outputting set might be smaller. That's why it's called a reducer. It's like a reducer in MapReduce speak. But sometimes it might be more. So there is no enforcement that it has to be smaller. And basically, all these UDOs are scaled out with explicit U-SQL syntax to make it easier for you to kind of see when it does, and it gives you the ability to pass in some additional schema parameters, etc., that it can take a look at. So let me now show you an example of this by basically taking the same images, but in this case, I wrote an extractor myself using the extraction framework to identify the EXIF properties and do a thumbnail creation of the image that I get passed in. So let's take a look at that code quickly. So here's the script. I reference my own assembly. That assembly is actually here in this project. So let me quickly zoom in. So this is called, I think it's called U-SQL code project for .NET or so. I can show you quickly how to create that. The main difference between this and the normal C# project is that it has some predefined references added, and it gives me some additional tooling help to register the assembly inside my Azure Data Lake store as a U-SQL assembly. So let me show you that quickly. So I could go here, select images, right-click on it. There is a register assembly option. I click that, and that will basically build the solution. And it basically gives me the ability to identify the Azure Data Lake Analytics account, where to register it, the database that I want to have it registered in, which assembly name to give, mark it if I already have a copy of it. And then down here, let me zoom in again, I can add additional dependencies. Now you see that we have three types of dependencies. We have managed dependencies, which is basically, if I have other .NET DLLs that I need for this, let's say I'm doing something with JSON and I use Newtonsoft.json, etc. I can mark the ones that I want to have deployed as well, and they get their own top-level registration as their own assemblies. Then I have additional files. In there, I might add additional dependencies that I need, like configuration files, like maybe a native DLL that I need, that I want to have registered together. And then the last one is the debug information. The debug information you want to register if you want to then make use of the local Vertex debug capability. So if you run a script and the script fails at runtime, you can download the Vertex that failed and do local debugging. If you have custom code in it, then what it means is this basically contains all the PDB files and all the files that help you do local debugging, even if you are doing it from a different machine than where you actually authored the script. So that makes it very easy to do debugging of like failed jobs and so on. So obviously I already registered mine, so I'm not going to do it again. So I referenced this up here, and now you notice my extract statement basically gets the copyright, equipment make, model, thumbnail, etc. It also gets the string and format again as earlier. My extractor here has some parameters, scale, that gives me the scaling information for my thumbnail. And then like before, I'm using my file set format filter here on line 20 to basically restrict it to JPEGs only. Then I split my output. The first output goes into a file, just where I extract these capabilities. And then down here, I also, take my thumbnail out, and I use a custom outputter to basically dump my byte array into a file as the thumbnail of this image. And then I execute that. So I did execute that too. Here's the job graph. One thing here, this job graph, I didn't use some of the combination features. So in this case, every vertex runs once on a file. So I have 15 input files, and I have 15 input vertices. So this job was not as optimal as the previous one. And if I look at my image features here, unfortunately, Visual Studio does not a good job at previewing JPEG files. It just gives me some garbage. But if I zoom in here, you will notice here are the different camera makes, Sony, Samsung, what camera model, etc. So you have a wide variety of information here that I extracted. So let's take a quick look at that code as well. So now this code is written down here in the image feature extractors. So this is just C#. So as you can see, it has the images namespace. And in here, the important part is the code down below here. So I basically implement the iExtractor interface, which is our API that you need to kind of implement against. In particular, I mark this one as a user-defined extractor that has atomic file processing set to true. Now, why is that? Well, we try to scale out your processing. And often, data formats might be splittable, like a CSV file. You don't care basically which row comes after which other row. They're completely independent, so you can split them and scale the processing out. So if you have a 100 terabyte or a 100 gigabyte CSV file, you can run it over 100 nodes, for example. An image obviously doesn't split itself. So if I have a really large image, I still want to have the whole image be seen, because otherwise all my capabilities of processing images probably doesn't work. So in this case, I basically say, well, this needs to be a single file per extractor. And then in here, I have two methods. The first one is I have my class constructor. That basically just takes the parameterization. So I can set default parameters as everything. And then down here, I have my extract statement. And inside my extract statement, what I do is I go and first use my system.drawing capabilities to get image version from the base stream. So I basically get the byte array. And then for the byte array, I do a little bit of magic here in terms of checking if my extract statement requested the corresponding column, then it will actually apply the lambda expression that I specified. Why do I do that? Well, this gives me the flexibility of basically doing column pruning. I do know what in my code, let's take a look at that extension method up here. I have the ability in my code to actually look at what is the schema that I'm requesting in my extract statement. So I can check, does this name exist in that? And if it does exist, then I go and basically apply the lambda expression to execute it. So that gives me kind of like an on-demand execution. Now, sometimes the on-demand execution, doing that check might be more costly than actually doing it anyway. But in this case, where I do a thumbnail creation, for example, or I parse my EXIF properties, it's probably cheaper to do the check and only execute the expression when it's really requested. So this should have shown you very easily how to do this. So how do you do .NET UDOs? We give you the API, you implement the interface. You can use any .NET language. We have 1 or 2 people that are crazy enough to use F# for doing so. And then you basically deploy the UDO, you register it with the tooling, etc. Now, the one thing is that the UDO can invoke managed code, and it can invoke native code that is together deployed with the assemblies. It can even invoke other language runtimes, and that's how we give you the the Python and R support. And we will scale it out. There are some limits, though. We are running them in a sealed-off container, so you cannot reach out of the Vertex into other web services. This is a no-no for that distributed denial of service attack issue that I mentioned earlier. Also, you cannot communicate between different UDO invocations, because that is non-deterministic, because there's no guarantee that one node will execute before the other. And so we want to avoid this non-determinism, because that can lead to really surprising results. Another thing is that we have some limitations. Like right now, the memory limitation inside the UDO for user-allocated memory is about 500 megabytes. So that means, for example, if you build your own XML extractor, for example, or JSON extractor, and you load the whole document into a DOM, you have to make sure that you're not running out of memory, because these DOMs are normally up to an order of magnitude bigger than the textual representation. So how to specify these UDOs? You could use what we call the code behind feature, which is a feature in Visual Studio that basically kind of hides this. I will show you that with the Python example in a minute. Or you can basically do this with separate class libraries, which we have seen earlier as the example. And the UDO model, just to recap, basically you implement the interface, you mark it as what it is. You have parameterization with the class constructor. You then override the extract method of the interface. You have a UDO-specific processing pattern, the one that you see here, which is, I think, not a really good one, actually. I need to fix the code there. is showing you, for example, how to do row-based processing. We should use input.split, not sread to end.split, because then we have issues with other stuff. I might need to go and fix that. And then we basically have even the ability to look at both the input and output schema if we want to see. So that gives us a little bit more control over what we actually operate on, because we can see the metadata, which is something that you can't see if you're just doing it in the SQL context. And then you can output and operate either by position or by name of the columns. We can create assembly, reference assembly. If you do have .NET framework assemblies that we don't preload into your Vertex, you can reference them with system assembly reference. And you will probably need to use quoted identifiers because of the dots inside the name. And you can enumerate assemblies in PowerShell, in all the explorers. We even now have catalog views, so you can look at it in catalog views as well. And then you can drop assemblies, and everything is made easier through, for example, our tooling. Another thing that we give you is sometimes you want to have script-specific resources, like a specific configuration file, a specific model that you want to apply for doing machine learning or so, that you don't want to register or store together with the assembly because it can change from invocation to invocation. Now, these files can be deployed as resources directly onto the Vertex and then accessed from within your custom code. So that gives you an additional way of parameterizing your custom code. These files have to live in ADLS or Windows Azure Blob Store, and they will be deployed. There are a couple of limits about how big an individual resource can be and how many resources you can deploy in a single script as well. So this looks then like this. So I have my U-SQL script, I compile it, optimize it. I have my reference assembly statements and my potential deploy resource statements. And then I basically create this package during compilation that takes my C# code and produces managed DLLs, takes my C++ code, produces native DLLs, the algebra file, any additional deployed resources, the system files, etc., all get packaged up and then shipped into the Vertex. So that's how this gets executed. So now let's take a quick look at Python. In this example, I have my tweet example. So I go and look at my tweets, and I extract the mentions and the topics of the tweet. So let's take a look at that. So here is the inline example. So in this case, I currently reference this extension Python library. This is also part of that U-SQL extension package that also gives you the cognitive services APIs and the R extensions as well. Now, this currently comes with a special reducer that basically takes either a script as a variable or a location of a file as a script. And in a specific extension Python reducer here. So this basically takes a script. Now, what does the Python code do? Well, remember, the Python code is embedded within U-SQL to be scaled out. So what it does is it basically takes a data frame in, which is the row set or the partition of the row set that we give that particular vertex. Then it does the transformation of that data frame into an output data frame using whatever Python method it wants. In this case, I drop some columns, and then I apply two Python methods up here that basically do the standard extraction that I mentioned, basically the tweeted at and the hashtag topics. Then I do a quick cleanup, and I output this. So the job did run here over 10 input streams, my 10 tweet files that you might have seen yesterday as well. And then I do this extraction here, the combiner, and if I look at the result here, you see basically like a topic and who was operating, who was mentioning, etc. Now, of course, there's additional cleanup needed because I was, like, my Python code only split on spaces and not on punctuations, etc. And it doesn't care about casing and some other interesting things. So this just shows you how easy it is to actually execute Python code. Now, I mentioned the code behind. So down here, for example, if I right-click on any of my U-SQL things, I can have this add UDO option that gives me the ability then to add a C# code behind, Python code behind, or R code behind. In this case, I did do my Python code behind here. This is exactly the same Python code that I had before. And in here now, I mention the name inside my reducer just as a string here, using the path name underneath here. And when I submit this, let me see, I basically does exactly the same thing. It takes about the same amount of time. But if I look at the code that got submitted, so I click on the script link down here, you will notice that now the code behind auto-generated like all the necessary code to submit it. So it basically does the inlining, etc. for you automatically. So this is just going through the same example. The link to the documentation is there. A few things I want to add to it. So we give you a lot of standard built-in libraries such as NumPy, scikit-learn, pandas, etc., that you can use from within Python directly. And probably later this year sometimes, we'll actually give you the ability to natively write your Python extractors and processors and appliers and all the UDOs without having to go through this interaction. So you're actually going to get better performance and even better scalability later this year. So this is just going through what I showed you earlier. So the difference now, if I do the Python code, is that I do a reference assembly extension Python, which will load the Python engine and libraries into the Vertex as well. So this is like in addition to all the stuff that you saw earlier. And the execution is basically, if I have a reduce stage, the reduce stage gets partitioned into multiple partitions. These row sets then are going into each one into their own vertex. And within that vertex, I have, and sorry for the color scheme here, I have, looks better on the laptop, I do have my Python R reducer. Now, in that, I basically have the data frame input, the R code or Python code that runs, and then the data frame output again. So these row sets basically run through there, type mapping happens, and then the row set flows out again from the data frame back into a U-SQL row set. So that's kind of how conceptually this execution model works. So the same happens with R. Now, in R, the interesting part is that you can use this to both generate a model as well as apply a model. Now, generating a model is a little bit problematic in the sense that it requires you, normally when you do a model creation, that you see all the input data. So what happens is, and I'll show you that at the bottom there, you basically have a single constant, 0 here, as the partition key. So that means you're basically having all the data come into one row. So why would you use a scale-out engine to do your model generation in R? Well, maybe you have different parameters. You might want to create different models that you then want to create in parallel, and then do the evaluation of the models, the testing of the models in parallel as well. So that's what the data lake would be useful for in this context. Again, the model is very similar to what we have seen earlier. We basically give you either the R script directly as a variable, or we give it to you as a file, and then you call it through the reducer there to get the result back. In this case, I generate the model, or I can also apply a previously generated model. In this case, I have to deploy the resource of that model as an additional resource. So remember the deploy resource statement that we had earlier. And then we basically go and load that inside my R script. and I use whatever ln-fit algorithm, for example, in this case, for doing the prediction. Input-output is the same as in Python. It's the data frame in and the data frame out. And now in this case, since the application of the model is not dependent on the on having all the data in a single column, because I basically apply that to every row, I get the ability to basically partition that and scale that out based, in this case, on some random number generator that just equidistance distributes the data over the different nodes. So this gives me a very easy way of basically applying, for example, R code, in this case, a model scoring algorithm, at scale over large amounts of data inside my lake. We have one customer, an insurance company, that is actually doing fraud prediction by doing exactly that. They have, I don't know how many hundreds of millions of transactions where they're applying R models to see for fraud. Oops, my focus is gone. So similar to what we have seen earlier, exactly the same. When I reference the extension R assembly, we do load the R engine, which is currently an open source R engine. We are looking into potentially getting better integration with Microsoft R Server or so in the future to kind of give you that integration. Now, there is no timeline associated to that statement, by the way, unlike somebody recently tweeted. So to summarize, I think you have seen now that you can very easily bring your own code. You write a thin wrapper around your code in one case that basically allows you to make that code fit into your into our model of providing data in and data out. And then you basically apply that to do your custom processing. That code can be in any .NET language. It can be Python. It can be R. And we are looking at other languages. So if you have a favorite language, maybe one that starts with an S or a J or so, let me know, and we can take a look at whether that's in our long-term plan. And then U-SQL basically gives you a very easy way of scaling it out if you are somebody that is familiar with SQL. It's a much easier way than calling extended store procedures, for example. If you have any further need to dive in, here's a set of links, including the ability to go and look at Microsoft Virtual Academy to learn more. There are the links about the R and Python documentation. And if you have any feedback or questions, you have our forums, both on Stack Overflow and MSDN, and our feedback page if you have any additional wishes or requests that we should be taking a look at. Thank you very much. If you have any follow-up questions, feel free to ask. Thank you. Any questions? Yes? So I'm not sure I fully heard it acoustically. So you were saying that there are like other algorithms like word stemming and so on. So this is more like for full text search type capabilities. I don't think they are currently included, so that would be a good like ADL feedback page thing to request that. Actually, full text search is close and dear to my heart because I owned it for a while in SQL Server. I added the semantic search capabilities back then in 2012 or so. So having more of that is definitely useful in a data lake environment anyway. So yeah, ADL feedback page. I will vote it up. And everybody else here as well, I guess. Yeah, any other questions? If not, thank you very much for joining me on this last session, and I hope you still have a great evening in Darmstadt. Thank you.